So now that we've talked about the absolute value inequality and the interval it represents, it's time to move on to the precise definition of the limit. And to start off here, I want to show you a graphical representation of what we're going to be doing here. So here's just a x squared function, and if you plugged in your value, you draw your line of the function, there's the output. And what you did with the tables is you had a left limit approaching from the left, and then you got that function value. And then you took some value from the right, and you got that function value. And so it creates kind of this L shape here. And as you chose your values to get closer and closer to 7, this L shape starts to get smaller and smaller. And so our hope here is that as we get closer and closer to 7, our hope is that the outputs will get closer and closer to some value. Now, of course, the limit doesn't always exist. And here's an example where the limit doesn't exist. So let's say we want our limit at 7. And if we approach from the left, then here's our input for the left. Draw it up to the function. There's our output. And then from the right, here's our input from the right. Go up to the function. There's our output. And as we approach 7, notice what happens to the outputs now is the outputs get farther and farther away. And that's because this limit is going to infinity. And remember, like the previous example, we want these lines to converge. That's our limit. In this case, though, the outputs are diverging, and so the limit doesn't exist. And graphically, this is what we are doing, and we're going to put some math to this then, and we're going to be using the interval absolute value inequality that we talked about in the last video. So let's start with another function here, just e to the x, and start writing some stuff down. So we have our point of interest, c, and then we'll draw this to the function, and if our limit exists, it'll be at this output. And then we had our left approaching from the left. And then we had our approaching from the right. And notice on the y-axis here, I am drawing an equally spaced interval. So this interval is centered about L. And so we're going to use our absolute value notation there. But also notice that this centered interval, when we draw it to the line and then draw it down to the x-axis, that it's no longer centered on the x-axis. And that will always be true when you have a function with curvature. Only a linear function will preserve the distances here. And then this blue, again, is this kind of L structure that we want to shrink. So if the limit exists, then as we approach C, our outputs should approach L. And so we want this structure to shrink and shrink forever until it converges on our values. So let's write some math for this. So here again is our kind of our outline of our structure. Again, C, and then our left limit, our right limit, approaching from the left and the right. And on the y-axis, we're going to create our centered interval. And so we're going to call this distance epsilon. And if that distance is epsilon, then that means the upper value will be L plus epsilon, and the lower will be L minus epsilon. So we're setting up our interval here. And let's stick in an input. So we have our x input. So this x would be the values you chose when you did the table. When you were making those tables, you were choosing these x inputs, and then you were finding out what their outputs were. Now on the y-axis, we have all our information to write out what this interval is. So again, notice it's centered on L. It has a tolerance of epsilon. And what we want in this interval is f of x. And so we can write that then with an absolute value. So again, L, here's the center of the interval. Epsilon is the tolerance, how far we can go away from L. And then in the function output, f of x, is what we want in this interval. And this is our expression for the y-axis interval. So let's check out the x-axis then. So I'm just going to look at a number line, and we have our point of interest C, and we're going to choose some delta distance away so that our lower point will be C minus delta, and this is going to be a centered interval. So to the right, we also will go delta. So we're going from C minus delta to C plus delta. And we'll have our x that is in this interval. So from previously, we have this expression for the y-axis. And now if we look at our information for the x, we see it's centered about C. It has a tolerance of delta. And what we want in the interval is x. And so we can write that then with our absolute value. So again, here's C, the center, delta, the tolerance, how far we can go away from C, and x is what we want in this interval. Now here's where we have to make a fix on this inequality here, is x approaches C specifically means you get forever closer to C, but x never becomes C. You can only get forever and ever closer. And what this means is that x minus C will always be greater than 0. And so we're just going to tack that on there as part of our definition for x approaching C. That x can never equal C. And so this will always be greater than 0. Now the book reverses this expression, which is there's nothing wrong with that. So what the book does is they take this expression here and they just reverse it. And so we have our two important expressions for the definition of the limit then. We have our interval that expresses the y-axis, and then we have our interval that expresses the x-axis. So let's check this out by putting it on a graph. So here's the function again that we started with, e to the x. And I'm going to put on the x-axis this interval that we just talked about. And then here's our inequality expression for that interval. And I'm going to start from C, draw a line up. Whoops. Start from C, draw a line up. Go over to the function. If the limit exists, this is where it'll be. And now we're going to create a centered interval about L. And so there we go. There is a centered interval about L. It can go epsilon up and epsilon down. So let's go over to where our x value is, and we'll draw a line up to the function and over, and there is the function output on that line. And now the y-axis has all our information to write out now the absolute value for that axis. So again, L, the center of the interval, epsilon, a tolerance, and the function output is what we want in that interval. So I'm just going to finish this picture up here. This line here, I didn't draw it down. And this line here, I didn't draw it down. So I'm just going to draw those lines down there. And then I'm going to fill this in. So I just filled it in from the outer lines. And now notice that our y-axis centered interval, when we draw it to the function and then draw it down, this is no longer going to be centered on this x-axis. So notice the yellow is no longer centered around C. And this will always be true when you have curvature. Only a linear function will translate this centered interval to another centered interval. And so our job here then is to choose a delta that will squeeze this interval into the yellow region. And so what are we doing here? Well, we have this yellow structure, and we're going to compress it forever. And we want to make sure that X is always in this yellow structure. If we can make sure X is always within here, then when we squeeze this yellow structure, we know X will be approaching C because it'll always be stuck in this yellow structure. And so that's why we want to try to squeeze this interval in here. We want to make sure we are always trapping X in here. So let me just make that smaller here. Here's our two important expressions again. And this is the process. Is you would choose an epsilon. An epsilon then creates this yellow structure, how big it will be. And then once you choose an epsilon, you want to find a delta that will squeeze this interval into the region. And in 3, if you can do this for all epsilon, then the limit exists. So in other words, for all epsilon that you can pick, if we can find a delta that will squeeze this interval into the yellow region, and we can do that for all epsilon, then the limit exists. And I want to say about this definition here, that the definition is telling you if this is a limit or not. The definition doesn't tell you how to solve for a limit. It doesn't tell you how to get a limit. And I know that can seem a little bit confusing, but if you think about the definition of a chair, the definition is something like it's an object you sit on, maybe it has 4 legs. The definition of a chair doesn't tell you how to get a chair. The definition just tells you whether this is a chair or not. And the same is true here with the definition of the limit. This definition is just telling us if this is a limit or not. It's not telling us how to get a limit. That's what we did in 2.2. So let's check this out with an actual function and see how all this works. So the function I do have drawn here is e to the x. And we're going to use our knowledge from 2.2 to determine what that limit is as x goes to 1. So e is a continuous function. We can just plug 1 in, and that is our limit. As x goes to 1, the limit is just e. Now, is this a limit? we're going to now check with our precise definition. So again, I'm getting the answer from the limit from something else. We're now going to check if this is actually a limit. And so we're going to use our information and plug it into our two inequalities. So first off, L, I'm saying the limit here is E. So I'm just going to change this L to an E. And we know the function is e to the x. So I'm just going to change the function here to e to the x. And if we go to our other inequality, we know that c is 1 from the limit here. X approaches c, so c is 1. So I'm just going to change that c to a 1 there. And here we have our two inequalities that we're going to focus on now. So we're going to focus on these two inequalities. And actually, I want to go back again real quick here. Our goal here is we want to solve for what is this intersection from the yellow region here. In other words, you can see I drew this box, this yellow box, but where does it start on the x-axis? What is it right here? And where does it end over here? This is what we need to figure out. We need to figure out where this yellow box intersects the x-axis. And so that's what we're going to do with this left expression, is we're going to solve this for x. And the first way we're going to do that is to get rid of the absolute value. And we can do that by breaking this into a double inequality. Remember, our goal here is to isolate x, so we'll add e to all the sides here, to every part. So I'm just going to add e. And now the center, we almost have x isolated. We just have to get rid of the e, base e. And we do that by taking the natural log of everything. So we'll take the natural log of everything. And then the natural log of e to the x is x. And here is our expression that we're actually looking for. Because this tells us the inputs for x. This is telling us the interval now. And so let me pull up the graph here. Here's our picture again. What we just figured out was where the yellow box here is intersecting with the x-axis. We just figured out that this very left point right here is natural log of e minus epsilon, and this very end point on the right, the largest value of the interval would be natural log of e plus epsilon. And that's what we just figured out right there. So let me just zoom on this. So just zooming in a little closer there. And then we have our logs here for where we have our intersects here. And now remember, to squeeze this x interval in, we choose the shortest distance from C. So from C, we have this distance to the right of the yellow. And then we have this distance here to the left of the yellow. And you can see then that this right one is the shorter distance. And what is this distance? Well, we know C is 1, because that was in the limit at C equals 1. So this distance here then would be the natural log minus this 1. That is this distance from C. And then that is our delta. If we chose this delta, then that would squeeze the interval into the yellow region. And that's it. That proves this is a limit. And how does it do that? Well, remember, we have to find a delta for every epsilon. And we just did that. That's this equation up here. whatever epsilon you give me, I can tell you a delta. And we can do this forever. And so then this proves that this is a limit. We can squeeze this yellow region forever, and this equation here will always tell us a delta that will squeeze our interval into the yellow region. So let's try another one. Oh, I have another picture here. I wanted to illustrate that again. So here's that blue picture from before. Here is epsilon as we squeeze the outputs. And here is what we just solved for. We just got this function for delta that represents this width right here. And as we squeeze this structure more and more, we always know what this delta is. And we can always find it just given an epsilon. So again, for every epsilon, we can find a delta. And then that proves that this limit exists. So here's the next one I wanted to try, x squared. And let's say we want to investigate this limit as x goes to 2. And from 2.2, we know this limit is 4. Now, is this really a limit? Well, let's check the definition. So again, for all epsilon, we want to find a delta such that these expressions are satisfied. So let's start with the absolute value expression for the y-axis. So we have f of x minus L. We know the function is x squared, and we know L is 4. So just plugging that in. And same for the delta one. We know C is 2, and so we're just going to plug that in. And so let's take a look closer at these two expressions. More specifically, just this one. This is the really important one. And we're going to get rid of the absolute value. And we do that by breaking this into a double inequality. And now our goal is to isolate x. So we'll add 4 to all sides. And now we just need to get rid of the squared part. And we can do that by taking the square root of everything. And now we've done it. We have solved for the interval on the x-axis. Here it is. X must be between these two values. So let's take a look at that on a graph again. So here's x squared. Here's our point of interest 2. We think this limit is 4. We'll create our centered interval on the y-axis. So we'll go up epsilon and down epsilon. And we'll draw that over the function and then draw that down to the x-axis. And here's our little structure. And we'll just fill that in. And this is what we squeeze forever. And then we want to check these distances. From the center point to, we want to see which is closer, the right side of the yellow or this left side. And we just figured out what those sides are. We figured out that this left side is at square root of 4 minus epsilon, and the right over here. And again, you can see the right side is the shorter side, and so that's the distance we want. And that distance then would be square root of 4 plus epsilon minus 2. That is that distance. And that is then our delta. And I did draw on here a brown line to indicate our squeezed in interval. So our interval here goes all the way to the right of the yellow, but it doesn't make it all the way to the left. That's fine. What's important here is the interval is in the yellow. And so now when we squeeze this yellow region forever, we know our x value will always be trapped in it. So let's check out another one. And I want to do this one for two reasons. First is how to handle 1 over x in a double inequality. And I also want to show you what happens when it fails. So I'm going to pick a false limit. This limit is wrong. So let's see how this works with the definition. So I want to know what the limit is as x goes to 1. Now we can just plug in 1. The limit here, the correct limit is 1. But let's check out what happens if you have an incorrect limit. So I'm going to say the limit is 2. Let's see what happens. So again, we want to see if for all epsilon we can find a delta such that these expressions are satisfied. So we know what the function is. It's 1 over x. We're claiming the limit is 2, and so we'll just plug that in. And also for our delta expression, we know c is 1. So here's our two important expressions. We'll focus on just the first one here, though. And again, our goal here is to solve for x. And the first thing you want to do is to get rid of the absolute value by breaking this into a double inequality. And then we'll add 2 to all sides. And here's the part I wanted to talk about. How do you handle this 1 over x in a double inequality? Because we can't just multiply everything by x, because then we'll have our x stuck on the outsides there when we want our x in the middle. So what I like to do here is take this double inequality and break it down into its two parts. So we can take this left part and we can take this right part and break it into two single inequalities. And now we can just solve these individually for x. So kind of like a cross-multiplying thing there. And now we can take these two pieces and put them back together into a double inequality. So if you look at this right one here, this is telling us that x has to be greater than this. So here it is right there, x is greater than that. And then this expression here is telling us what x has to be less than. And so we can stick that over here. And so this shows then that this left expression, this 1 over x, we can write this as this expression here on the right then. And so that's how we go from 1 over x to getting that x isolated then in the center. And this is our expression then. So our absolute value expression, we can break down to this double inequality. And now let's check this out on the graph. So here is 1 over x. And we'll stick on our point of interest, which is 1. And then we go to where our limit is, which we think is 2 here. And then we draw our centered interval around 2. So we go up epsilon and we go down epsilon. So there's our centered interval. And then we'll draw these lines down to the x-axis to create our little structure here. And now notice that 1, our point of interest, is way over here. It's way outside of our structure. And remember the goal is to choose a delta that will get this interval into the yellow. But we can't move the interval. We can't move the number 1 to over here because this is the number line. This is where number 1 exists. We can't move number 1. So there's no way for us to choose a delta that will get 1 into the yellow region. There's no delta we can choose here. And so this is not a limit. We can't find a delta that will get 1 into this interval. And something else I want to point out with this inequality here, this double inequality, is think for a moment as epsilon goes to 0. Oh, I'm sorry, here's the brown line. I was drawing this interval out there. So this interval, there's no way we can get this interval into the yellow. So if we imagine that epsilon is going to 0 in this expression here, you can see that this expression would actually go to 1/2 here. And this is actually telling us what x should be if we had a limit of 2. So if our limit is 2, which we're saying it is here, then we should have an input of 1/2. But either way, there's no way we can get 1 into that yellow region. There's no delta that we can choose, and so this is not a limit. And so there is the precise definition of the limit. It's about 2 intervals, the y-axis and the x-axis, and then we try to squeeze the x-axis into our structure. And so as we shrink the structure forever, we know x will be trapped in it. And that means that x approaches c, and then our outputs will be approaching L. And if you want to see some more examples of this, I'm going to do another homework helper for this, doing some of the homework problems. And I will talk to you in the next video.